This is Engineer Management 615, Nonparametric Statistics, and this is week 2's lecture video. This week is about chapter 2, some fundamentals of nonparametric methods. In this course, I assume that you are familiar with most fundamentals in parametric methods, that is statistics 1 and 2. You don't have to memorize every details of every term. If there's a term that you heard of, but do not remember its exact definition and features, just stop the video and look it up, because we may not review everything during the lecture. And for these terms, it doesn't matter because we will not expand those things. Those are just examples. Usually for a parametric method, there is often a corresponding non-parametric equivalent. And the difference is that nonparametric method has weaker assumptions on the data, especially it has no assumptions on the particular distribution or distribution family of our data. So these methods are usually more robust to distribution assumptions. So first, let's look at a method called permutation test. Using parametric methods and non-parametric methods, we have hypotheses and test our hypothesis. The hypothesis can be about the mean value, comparing two mean values, the variance values, comparing the two variance, the variance of the two samples. So, or comparing the mean or variance of one sample over the whole population. So through those testing, we either reject or accept the statement in the hypothesis, in the null hypothesis. So with the testing result and some other analysis using the samples, we can infer some information about the whole population. So for the purpose of doing this hypothesis test is when we do not have access to the whole population's data, we only have a sample data, but we really want to know the statistics of the whole population. Therefore, from the sample data, we have the sample statistics, and using those sample statistics, we make those hypotheses and do some testing. So we know about the population statistics. So through the test, we for parametric methods, we have some inferences, but those inferences often have assumptions that our samples may follow some distributions or distribution families. Whereas using non-parametric methods, those inferences have weaker assumptions, usually just the assumption about the symmetry, symmetric features or continuous features of a sample. So with those weak assumptions, the distributions of the samples may not matter that much. We can have different distributions of the data, but still verify whether their location or spread is what we thought. So let's look at an example using permutation test. So this is example 2.1 in our textbook to test the efficacy of a new drug versus a standard old drug. So we select 4 patients out of 9 to use the new drug, and the rest of 5 patients are given the standard drug. So the 4 selected patients are, usually we call it experimental group, and the rest of 5 are the control group. So after some time, all 9 patients are examined by a consultant. That consultant, with his or her experience and some historic data, he or she does various tests and observations. Based on those results, the consultant ranks the patients from 1 to 9. 1 means most satisfactory, 9 means least satisfactory. If there's no beneficial effect of the new drug, then what means the new drug has the same effect or worse effect versus the standard drug? Then what is the probability that the patients, the 4 patients who receive the new drug are ranked 1, 2, 3, and 4? So intuitively, this probability should be very low, right? Because if the 4 patients using new drugs ranked like this, we may think that the new drug has a better effect than the standard one. Why? Because if the 2 drugs have similar effects similar effects, then there are 126 ways of picking 4 from 9, the ranking. 124 ways, and each of them has an equal probability. So why 126? This is combinatorial. Combinatorial is from a n number. We pick r, and what are the combinatorial results of them. It can be written as either this is a huge parenthesis from 9, select 4, and what are the ranked results. And for this also we can write it as a big C with a footnote 9 and with a super note 4. These two have the same meaning from 9 sample observations. We select 4 of them. And the equation to calculate this value is here. For this problem, n equals 9 and r equals 4. And the result is 126. So if the new drug has no effect, then the 4 patients ranked as 1, 2, 3, 4 is just a 1 over 126 chance, as equal as other ranked results, right? So here in this table, they list all the 126 ranking results of the 4 patients. And also they have a sum of the ranks by the end of each outcome in the parentheses. For example, if the 4 patients ranked as 1, 2, 3, 4, the sum of this 4 value is 10. They write it down like this. And what's the utility of this number in the parentheses? We'll talk about it later. So for now, we just ignore it. And if the new drug has no improvement compared with the standard drug, then these outcomes would have equal chance, right? So it is more plausible that this outcome 1, 2, 3, 4 is more likely as a result of a beneficial effect of the new drug, right? Because the probability is very low if there's no effect. So given that, let's do a hypothesis test. But the hypothesis test is a 2-sided one, because this time we do not only test if the drug has a beneficial result. We want to know if the new drug has either positive or negative effect versus the standard drug. So in that case, the null hypothesis is new drug has no effect. And the alternative hypothesis is new drug has an effect, either beneficial or deleterious result. So it's a 2-sided hypothesis test. So if that's the case, then we have 2 extreme outcomes. One is when the 4 patients ranked as 1, 2, 3, 4, ranked as the first 4 places. And the other is the opposite. The 4 patients ranked as 6, 7, 8, 9, the very last 4 places. So if the null hypothesis is true, then all 126 outcomes have equal probability, as we talk about. So then each of these 2 extremes has only 1 over 126 chance. So their total associated probability is 2 over 126. This is a low value, 0.0159. And in parametric hypothesis testing, or sometimes we call it classic hypothesis testing, if the ranking outcome of the 4 patients is 1, 2, 3, 4, we would take the p-value as 1.59%, just as this value for two-sided test. Suppose we use a 0.05 alpha, and alpha is significance level. The p-value is smaller than that, right? So we should reject the null. However, for our problem, since the ranking outcomes are not continuous, we have ranked as 1, 2, 3, 4, 1, 2, 3, 5, or 1, 2, 4, 5. So those are kind of discrete. They're all integers, and there are 4 of them. Then what is the p-value of this outcome? What we can do is we can introduce another statistic, and that statistic is a function of those 4 ranks. In this way, we can convert the 126 outcomes to different values of this single statistic. Therefore, we can calculate the test statistic and p-value of any ranking outcome listed here. So we can decide whether to reject the null hypothesis using those p-values. And the number in the parentheses are those sum of the 4 ranks, right? So different ranking outcomes may have same sum value. For example, here 1, 2, 3, 6, the sum is 12, and here 1, 2, 4, 5, the sum is also 12. So what we care is for each sum rank sum, how many times it occurs in this 126 outcomes. Therefore, we can list those rank sum with their occurrences like this. The occurrences are very important because using the occurrences, we can calculate the probability of each rank sum, right? So sorry, I have a sore throat, so I may clear my voice from time to time, which is annoying. Just forgive me. So using this table, given any ranking outcome with the rank sum, we would know that how many outcomes are better than that, right? And this is the rank of each ranking outcome. Therefore, we can get the critical regions for various significance level alpha. For example, if alpha value is 0.05, suppose it's two-sided, then we use half alpha as each side, each tail, which means half alpha is 0.025. You may have noticed that the occurrences of these rank sums are symmetric, right? For the low value, 10, 11, 12, 13 is 1, 1, 2, 3. And for the highest 4 value, it's also 1, 1, 2, 3. So it's a symmetric data set. Therefore, we can use one-sided result and double it, use it as the two-sided. So anyway, for half alpha equals 0.025, we use 0.025 multiply 126, which are all the total occurrences of all the outcomes. And that result is 3.15. So among all 126 outcomes, only 3.15 best ranking outcomes and 3.15 worst ranking outcomes are in the critical region, which means we need to reject the null if the result is in those two regions. That is when the rank sum is 10 and 11 and 29 and 30, right? Because only 10 and 11, the cumulative rank sum is 2. But if we involve 12, then the cumulative occurrences is 4. 4 is larger than 3.15. So we should not include 12. So we should only consider 10 and 11. And that's the similar case for the upper tail, 29 and 30. So that's when we use alpha, the significance level, to determine whether to reject the null. And also we can use the p-values to help determine whether to reject the hypothesis. Using p-value for we can use it as one-sided or two-sided. Let's talk about them one by one. So for one-sided problem, suppose we want to test if the new drug has beneficial effect. So we or no effect. So that's one-sided problem. In that case, we favor low ranks of those 4 patients, right? We favor low value of the rank sum. So if the rank sum is in the lower half, then the p-value should be big. So we use 1 to subtract. For example, if the 4 ranks as 2, 3, 4, 5, then the rank sum is 14. 2, 3, 4, 5 is what is given in the textbook as this example. Let me go back to the textbook quickly. Yeah. This is just an example. If we want to test if the 4 ranks are 2, 3, 4, and 5, then whether we should reject or accept the null. So if the 4 ranks are like that, then the rank sum is 14, right? So for a two-sided problem, we double 14, so it's 28. So 28 over 126 is 0.22. So 0.22 is the p-value. For one-sided problem, suppose we want to test if the new drug has beneficial effects. So we favor low rank sum. So if the rank sum is in the lower half, then the p-value should be big. So we use 1 to subtract 14 over 126 as the p-value, which is 0.89. On the contrary, if we want to test if the new drug has deleterious effects, then we should just use 14 over 126 as the p-value. So that is 0.11. So this is the permutation test. Yeah. Sorry. This is the permutation test. It has another name, randomization test. When the sample is random selected, then we also can call the permutation test as randomization test. So in example 2.1, because the sample is small, we only have 9 patients, we call it pilot studies. Why do we not use a larger sample size? Because in the new drug development process, usually we first have a pilot studies, use just a small group of patients to do some experiments. Then if the drug is tested as beneficial effective, then we can involve more people to do a test with a larger sample size. Therefore, we can minimize the risk for this new drug. So when the sample is small, the result is somehow not very plausible. Right? You may observe that there's a lot of jumps between those outcomes, between those rank sums. However, since it is an early stage to test the drug, if in a pilot study a drug is proved to be effective, then we can continue with a larger experiment, and the larger experiment with larger sample size will be more effective. So next method we introduce is binomial tests. So why, when, and how do we use binomial tests? Let's look at an example to learn it. Remember this example we used in last week? That is, there is a censored observation, and we want to test if the median of the survival time of a disease is 200 months. Now, let's consider a test to justify that conclusion. We can count the number of observations in this sample with a value higher than 200. So that is from here, those three observations. This counting result should follow a binomial distribution, right? Because for each patient, there are two outcomes. Either he or she survived over 200 months or less than 200 months. So we have 10 patients, 10 observations, and for each observation, there are two outcomes. And for now, the probability of each outcome is 50%, right? Either above 200 or not above 200. So this is a binomial test. N is 10. 0.5 is the probability of each individual has a over 200 month survival time. So then we can use the binomial distribution probability equation to calculate all the results from 0 patients survive after 200 to all patients survive after 200 months. So each of those integers, so R can be any integer between 0 and 10, right? So the probability of each outcome is listed here in this table. And you may also observe this is a symmetric distribution because we have a 50% outcome of either way. Therefore, we have a symmetric distribution. Otherwise, if P is not 0.5, then this should not be symmetric. All right, so in this example, we have 3 observations exceeding 200. And we need to calculate the tail probability as the critical region. So we sum the probability of having 1, 2, and 3 observations exceeding 200, which is we sum 0, 1, 2, 3 probability, right? Yeah. So we should sum the corner results. That is a cumulative probability. That is the sum of these 4 values, which is 0.1719. And this is the p-value. So since this is a two-sided problem, then the probability distribution function of the p-value should be doubling of this value, right? So that is huge. That is 0.3438. So we have a 34.38% probability to get such a result, which is we have 3 people survived longer than 200 months. That is a huge value. Therefore, we should not reject the null, right? So for this test, we call it sign test. The sign test can be used to test the hypothesis on the population median. It is a simple and useful method. Using sign tests, we do not assume the distribution of the observations of the original observed values, but we do have assumption of a binomial distribution to calculate the probability of the counting result of those observations, right? But this assumption is the assumption of the binomial of the counting result is much weaker. You may have noticed that in a sign test, because the sample data are counts instead of a exact observed value, how many months. So the counts are discrete. So the p-values are also discrete. And that is different from parametric test, such as t-test. In t-test, the p-values are usually continuous. So using the sign tests, we can also establish a confidence interval for the permutation median. However, because the p-values are discrete, the smaller the sample is, the more sparse p-values we have. So the sign test is imprecise because of the discretity of the p-values. So let's look at another example to get this imprecision. Example 2.3. Again, use the same data set, which one of them is censored. So when R is any integer between 2 and 8, then when patients survive, which means between 2 and 8 is when patients survive between 58 months and 281 months. And this interval is with the probability using 1 to subtract the probabilities of getting 0, 1, and 9 and 10, right? So which is 97.84%. How do we get that? That is, here are the probability of getting each value, right? Between 2 and 8, the interval is between this one and this one. So we simply deduct the probability of getting 0 and 1 and 9 and 10. So that's the probability of falling into this interval, right? And that is, let's go back to slide 13, sorry, slide 12. And that is 97.84%. So this is the confidence interval, this 58 to 281. This is the confidence interval of a theta. Theta is the hypothesis, the value of the median, the population median of the survival time. So we would accept any null hypothesis that specifies theta in this interval between 58 and 281. So you may observe that this is a huge range. If any hypothesis cannot be rejected, which means the range is too huge, and then our hypothesis does nothing, right? It's not effective. Any hypothesis between this value, we would just accept it. So the median is some kind of disease survival time. The median is between 58 to 281 months. So if we tell the patient this information, it's not quite plausible, right? It's telling them you may survive 5 years to a 20-some years. They are still concerned about how long can they live, right? So this is called the imprecision of this binomial test. And we can see that the estimate lacks precision. So another difficulty is due to the discontinuity of the p-values because the p-values are discrete values. If we only regard the evidence against the null hypothesis as strong enough to reject the null using the p-value less than the significance level, then we regularly use in a parametric methods, usually we use 0.05 as alpha, then we may never get that evidence strong enough to against the null because no outcome provides it. Let's look at another example showing this difficulty, example 2.4. So in a dental practice, experience shows that 75% of adult patients require a treatment following a routine inspection. And another 25% of the adult patients do not require this treatment. So suppose we have a sample of 10 independent patients. So the number of individuals requiring the treatment, we use S to denote it. So for this sample, it also follows a binomial distribution. The only thing is the p is lowercase p is 0.75 instead of 0.5, right? This is the probability of any individual requiring this treatment. And for 10 independent patients, the sample size is also 10. So again, the number of people require the treatment, we use R to denote it, and R can be any integer between 0 and 10, right? But the probability varies. Using the binomial PDF, we can get the probability of all the R values here. And this is not symmetric, right? Because P is 75% or 3/4 instead of 50%. It's much easier to get a large R value than a smaller one, given the P is larger than 0.5, right? So for a non-symmetric distribution, we cannot, if it's a two-sided test, we cannot simply double the probability. We should calculate each tail and sum them, right? So anyway, our problem is not a two-sided one. Now, suppose we have data for another practice. We want to test for that practice if the chance for a person to require the treatment is larger than 75%. So the null hypothesis is P equals 0.75, and the alternative is P is larger than 7.75%. So this is a one-sided test. The smallest p-value is when R equals 10, right? We want to know if it equals, the other test is equal to 75%. So we favors when it's equal or smaller, right? But what we do not favor is when R is a large value. That may probably indicate P is larger than 75%, right? So the smallest p-value is when R equals 10 in that case, and the p-value is 0.0563, and it's even larger than 0.05 of our alpha significance level, which means with the sample size as 10, we can never get evidence strong enough to against the null. Even the smallest p-value is larger than the significance level. And in this case, a sign test is ineffective, right? However, if we increase the sample size from 10 to 20, this problem may be solved. But sometimes we just have a small sample size. So sign test does not work quite effectively for those small size sample. So that's binomial test. And then let's learn more about order statistics and ranks. So given we have detailed observations of a process, many non-parametric procedures are based on the ordering or ranks of those observations instead of just the real values of those observations. For example, median is an order statistic. And if we have an n observation sample, x1 to xn here, those are the real value of those observations. And each observation can be uniquely ordered from smallest to largest. So we assume each of them can be uniquely ordered. There's no tie ranking. So then we can represent the order observations as this: x with a footnote, a number in the parentheses as its rank. So the ith observation is denoted as x with a footnote of I in the parentheses, like this. And I can be any integer between 1 and n, right? And they are called the order statistics. So I refer them as x parenthesis 1, x parenthesis 2. And so in this case, x parenthesis 1 is the smallest observation, right? Because it's ranked from the smallest to the largest. And what's the utility of those order statistics? In this case, we can do sample distribution analysis using this order statistics instead of the real observations. It simplifies our problem. So the x parenthesis 1 is the minimum value of this sample. Sometimes we study it when we want to know the minimum extremes, such as the quickest machine breakdown or the minimum survival time of a disease. And x parenthesis n is the largest, the maximum extreme, right? And we use it when we care more about the large extreme. In some examples, such as the maximum flood levels recorded in the river over a number of years, or the maximum life of some product, etc. So given the order statistics, we have ways to measure the location and spread of a sample, right? So remember, when we have a sample, a data set, what we care is location, spread, and sometimes shape. So in nonparametric statistics, we first talk about location and spread, because shape is more related with the distribution or distribution family, which we do not care much or assume much in nonparametric. So the way we measure location for nonparametric is median instead of mean, especially when we use order statistics. The median is useful when we measure location. With the order statistics, we can get to the median even with censored data, right? If the sample size is an odd number, then we use this half of the n plus 1. This x parenthesis half of n plus 1. This is the value right in the middle, has the middle rank as the median. If the sample size is an if the sample size is a even number, then we use the average of these two in the middle as the median of the sample. So to measure the spread, we can use range or quartiles. Range is the difference of the maximum and minimum, but is sensitive to outliers, right? We do not exclude outliers when we calculate range usually. And quartiles are preferred since they are less influenced by the outliers, right? So in nonparametric statistics, an important concept based on order statistics is sample distribution function and or empirical distribution function. We use SDF for short, and we use capital S with a footnote N to represent it. Its corresponding concept in parametric statistic is cumulative distribution function, CDF, not PDF, right? PDF is a probability distribution function, not cumulative. So we use capital F to represent CDF, remember? So we use lowercase f to represent PDF. The equation to calculate SDF is this one. Given a value x, its sample distribution function value is using the sample size n to divide the number of sample values that are less than or equal to x. So SNX should be a value between 0 and 1, right? So SDF is not a continuous function because we use order statistics. They're all integers. And it looks like stairs like this. The horizontal axis, so this is sample distribution function, and the horizontal axis shows the ordered data, but here it shows the real value of the ordered data, real observed value of the sample. And the vertical axis shows the cumulative probability, or the SDF value. The larger the sample size is, the more steps the step has, and each step is smaller, right? Suppose there's no tie ranking. Every observation has its unique rank. And an extreme case is when we have infinite observations in a sample, then its SDF should be a smooth curve, right? Another extreme case is when we have only 2 observations in a sample, then the SDF would be having only one big step like this, right? So if X is less than the smallest observation in the sample, its PDF value would be 0, because no number of observations in the sample is larger than or equal to X. And similarly, if X is even larger than the maximum value in the observation, then its SDF should be 1. And any value in between its SDF should be a value between 0 and 1. So as I said, sample cumulative distribution function has a corresponding concept as in parametric statistics as the cumulative distribution function, CDF. So let's further look at their relations. So for any sample with the real value of the observations, there is a population cumulative distribution function, fx, capital Fx. And if we obtain the order statistics of this sample, we can get a SNX, that is the sample distribution function. So these two things are related. The mean value of SNX is a constant estimator of Fx, right? Sorry, the mean value or expected value of SNX equals Fx, and the variance of SNX can be represented as this function using Fx. And then SNX is a constant estimator of Fx for any fixed x. So why we get this, how we get this? Just think SNX as a piecewise function, and it is a piecewise function because they have steps like this. And then Fx is its linear approximation when n is very large. So you can get these relations. Then let's learn or review some tools to explore data. Those basic tools are the same tools when we use in parametric statistics. Now we use them again in non-parametric. So let's first look at an example using descriptive statistics to compare and explore several data sets. The story and the original data sets are in Appendix 1. And this is an example we use several times in this course. So this is the first time. Let me first introduce it. Then I will skip the introduction when we revisit this example. There are 4 Scottish clans in a district of Wester Ross in Scotland. They collected the age at death of male members of each clan, and they used a fake name for each clan to protect their privacy. But in their data, they have different number of members for each clan. The sample size is different. This is 59, this is 24, this is 21, this is only 13. And we summarize they summarize the sample statistics for each clan here in this table. From these statistics, we may find or intuitively find the clan with a relatively longer life expectancy. For example, Gamma. It has a larger mean, larger median, relatively small standard deviation, and it does not have any individual die as an infant. 0 means they die before their first birthday, so they die as infant. Although maximum death age for McClan is not as large as the other three, these two. However, this also may be because of a smaller sample size. And we need more scientific methods to do more thorough comparisons using these statistics, right? Because by only reading those numbers in this table may not give us an overview of the comparisons of their life expectancy or the shape of the distribution, right? So more statistics we care are quartiles. The first quartile is the observation at the 25th percent of ranking, and the second quartile is median, right? 75th percent rank is the third quartile. So for the quartiles and median, a large value may imply a longer life. A longer life expectancy. However, the IQ range is the difference of first quartile and third quartile. For this value, we desire maybe a smaller one, which means the sample is not quite widespread. To make the analysis more easily, we may need some visualization tools to help us read the statistics for more information. Let's look at box plots. We can show and compare the quartiles, range, max, min of those samples, and get quick findings. We can have each sample drawing into a box. So we can also look at whether the distributions are symmetric or skewed, how much skewed. For example, this one is more skewed than this one, right? And then, however, using box plots, we only divide each sample into 4 groups, with each group has a 25% observations, right? To further analyze more smaller groups of similar ages. I mean, if we divide the age group into 5 years or 10 years, box plots cannot show that, right? So we need more visualization tools. Histogram. So in histogram, we can further divide each sample in smaller age groups, such as 10 years, and look at the detailed distribution of those age groups. We can use histogram for each sample. This is for alpha. And we compare the histogram of different samples to get some conclusion and more about the characteristics of the sample. So the long tail to the left indicates the young age death are rare cases, right? It forms a more normal lifespan when the death age is around 80, right? Maybe from 50 to 100 is more like a normal distribution. So just as the sample distribution function SDF is an estimator of the population cumulative function CDF, histogram can be also used as an estimator of the population probability function PDF, right? So if the PDF is a curve like this, then the histogram is just changing the curve to the bars. And then, so we have learned that SDF can be a consistent estimator of the CDF, right? So as the sample size increases, the SDF mirrors the CDF more closely, right? Because it has smaller steps, more steps. This does not matter what distribution a sample forms, right? And for any distribution, we can use SDF to estimate CDF. So let's look at an example of exponential distribution. Example 2.6. So using computer to generate a sample of 50 observations following a certain distribution. Let's say this is following a exponential distribution with mean 2. So first, let's recall your memories. Exponential distribution is using lambda to time e to the power of negative lambda times x. Both the mean and the standard deviation of an exponential distribution are 1 over lambda. So when the mean is 2, lambda equals 1/2, right? So this curve here is the PDF of this exponential distribution. And these bars here are the histogram of the 50 observation sample generated by the computer with this distribution. So with a larger sample size and a smaller bin, the histogram can do a better estimation of the PDF because there would be more steps and each step size would be smaller. But even with a small sample size and a large bin, the histogram can still estimate the PDF, right? It's just the steps would be large and there would be less steps, not that accurate estimation. So if you remember, for histogram, we can also use cumulative histogram. That is, for each bin, we show cumulative probability. That is the probability of the sum of all its previous bins and this bin's own probability. And the shape of a cumulative histogram would be similar to the sample cumulative distribution, SDF, right? But there are differences. The differences are a cumulative histogram shows the cumulative counts or occurrences in each bin. So all the steps of this stair would be having same width because the bin width is determined by people as a constant value. But an SDF shows the order statistics, which are between 0 and 1, and the steps have different width, and the width all depend on the distance between the value of the ordered observations. So for an exponential distribution with mean 2, here is its CDF, this curve. And if we generate only 8 observations in a sample following this distribution, then here is its these steps are its SDF, sample distribution function. Even with only 8 observations in the sample, this SDF can also be used as an estimator of CDF, although some steps are big, right? And some steps are small. So that is different visualization tools. So we talk about the efficiency or the power of statistical tests. So let's talk about them again, because we really want to know the power of sign test of the non-parametric tests compared with the classic parametric tests. There are different factors, several different factors that may affect the efficiency of a test. So here we summarize them, not on the slides, but in our textbook. First, the power of the test depends on the sample size, right? A larger sample size may make the test more powerful and indicative. And the choice of p-value and significance level also affect the efficiency of the test. And the magnitude of departure from the null hypothesis also is a factor. And also the necessity of assumptions. If we have to make a lot of assumptions, that would make our test less powerful. So intuitively, tests have good power to detect obvious alternative, right? This is extreme small or large observed value would be easy to detect. So those the values far away from a specified value in the null hypothesis would be easy to detect as the strong evidence against the null, right? However, sometimes we care more when the alternatives are close to the null, right? Because if it's too far away from the null, even without a hypothesis testing, intuitively we can get some conclusion. However, when the alternatives are closer to the null, we cannot intuitively tell that. We have to use the scientific method to test. As the sample size increases, the power of a test for the alternatives close to the null can be increased, right? We always desire more data because we can get more information from those data. To compare the efficiency of two tests, there is a man called Pittman introduced a concept, asymptotic relative efficiency, and ARE for short. So using ARE, I'm not going to go through the details about the ARE because our course is more about a application course other than a theoretical one. Therefore, just to remember the result. Using ARE, the sign test relative to the t-test. T-test is a test we use often in parametric statistics, and it is proved to be the most efficient test in parametric statistics. All right. So using ARE, the sign test relative to the t-test is as low as 0.64. It means the efficiency of the sign test is lower than t-test. The performance of the sign test at small sample sizes is lower than big sample sizes. However, more often than not, we do have small sample sizes, so we use the sign test. If we have a lot of data, sometimes we may not need to use the nonparametric statistics, right? So this is a paradox. So valid t-test, which means when you use t-test appropriately, correctly. So valid t-test is the most powerful test for any mean specified in null hypothesis against any alternative hypothesis. But if our sample has a much longer tail than the normal distribution, for example, the double exponential distribution. So for those long tail distribution, sometimes we don't even know what distribution it has, but it just have a long tail. Then for that case, a sign test with a sample size n is as effective as a t-test with sample size 2n. Which means for long tail data, sign test is more effective. So again, but the sign tests may not work efficiently for small samples. It only works efficiently when we have a long tail and we desire a large sample size. So then in section 2.6, the textbook talks about computer software packages. But since we will introduce them, we will have tutorials to introduce them, especially R packages. Therefore, let's skip this section for now. So homework in chapter 2. I still prefer handwritten homework, but later when we introduce R, you may submit your R code. So for now, still write them on the paper or your notebook and scan them and upload to D2L. So homework 2, with these 6 problems, some of them have solutions keys in the appendix, some of them don't, but they are all very basic, and the due date is June 24th. All right, that's all for this lecture.